Well, good morning, everyone. Welcome back to our ESA webinar series, sponsored by our good friends over at Situ, helping us keep these free. And today's webinar is sponsored by Ivy Sol and Ivy International. Just some housekeeping before we get started. Reminder that the presentations and recordings, I'll get a copy of Bud's presentation as a PDF. It will be posted at esa.org/webinars, along with a copy of the video. Video takes a few hours to process, so it'll be up later today at esa.org/webinars. Reminder, Envirotech starts tomorrow. We have 27 presentations over 2 days, 14 hours of potential PD if you need it. All the sessions are recorded for those that pay to attend. It's only $49 for members, and there is room still left. We have a great response so far, and we really appreciate the support. So today, our good friend Bud Ivy at Ivy International is going to be speaking to us on effective in situ LNAPL and DNAPL site remediation using surfactant enhanced remediation technologies. So I'm going to turn it over to Bud. Bud's going to speak for about 45 minutes, and then I will be jump back online to do Q&A with Bud. So Bud, I'm turning it over to you. You should have control.
Okay, and there we go. I'm just getting my PowerPoint. You see that okay, Joe?
Yeah, just make it presentation mode full screen, and you are good and sound good. Thank you.
Okay. I'll get that out of the way. Okay, no, I'm just trying to get the panel for the event off there. Okay, Joe, I'm going to get my presentation up. All right, everybody, I'd like to thank you very much for taking the time from your schedules. I'm finding, although people are working from home, some of them saying they're feeling busier than they were before. There's a lot going on with the COVID-19 pandemic and how it's affected a lot of us at work. But I'm happy to see that I'm actually in Vancouver, so I'm glad to see that Alberta and BC, particularly in Western Canada, are coming back, and we're getting through our phases, and we're slowly step by step getting back to a new normal, so I'm very happy about that. So today I'm going to take some time to really do more of an educational type presentation about LNAPL and DNAPL remediation, because they tend to be very challenging. It's not just an issue we're dealing with here in Canada or United States, but even Europe's having their issues, Australia and Asia. So hopefully I'm going to share some ideas on how to look at them differently and hopefully change the way that you might consider typical ways of treating them. So moving on, I'd like to thank ESA for being very kind to put on these platforms. And when Joe first mentioned he was doing it, I thought it was great because it's a nice way for us to stay in contact with all of you guys and keep that exchange going on. I'd also like to recognize Chemco, who also helps us nationally to get our products to the marketplace. And to those of you who know Jean Perret, I'm sure he's on watching right now, so he's here to support as well. All I'm doing with these couple images just show different situations. This is frac sand before and after, actually from Alberta that we've treated. This is actually a refinery in Western Canada, and before and after soil, so you can deal with some of this stuff. As Joe said, I'll be making my PowerPoint and PDF available for everyone. And he's got a video of this as well that'll be recorded, so feel free to look for that. If you have any specific questions, my contact information, most of you have, but it'll be on one of the final slides, so feel free to reach out to me if you have those beyond the Q&A today. I'm very happy to inform everybody this is very fresh, and I thank Joe for putting a note in last week's newsletter. We made the top 10 environmental technology solution providers 2020 as a national award in the United States for a lot of the large brownfield and Superfund site work we're doing, so we're quite proud as a Canadian company to get that. And another company called Saltworks, actually out of BC, was also recognized in that top 10, so nice to see some Canadian technology getting some recognition there. The last thing I was going to say is, I mentioned this to Joe before, given all the COVID stuff and the impact to our industry, which has been very profound, I spoke to Jean Perret in that we're going to do something for our Canadian clients, and that for the balance of this year, we're going to offer a 5% preferred client discount on our products. So if you're reaching out to us, and Joe's going to give me a list who attended, you got to stay in for the whole thing. We will then offer to those individuals only. So it's just a unique thing for you for being kind to jump on today. A couple things that are becoming very important, and I'm hearing more about it in Canada, United States, and in Europe particularly, is the concern about unwanted impurities in products. And let's say you've heard about industrial grade, commercial grade, medical grade, research grade. As you go from one end to the other, there's less and less impurities in there. So I'm very happy to say, because I'm an organic chemist, purity means a lot to me and always has. Our products are very pure. So our PFOA, PFOS-free, 1,4-dioxins, PCBs, dioxyfuranes, and we've been tested and free of the long list of US EPA regulated compounds. If a new compound comes up, and there's been a couple in Europe, we add them to a list, and then usually the first quarter of every year we'll analyze those, even though we know we don't have them, just so we can keep our clients content that we've checked for that. Now, when we get into LNAPL and DNAPL contamination, we all tend to have this really simplified view. We know that they're non-aqueous liquids, and if they're light, they tend to float. If they're heavy, they tend to sink. It's not quite that simple. Yes, they have a tendency to float, a tendency. There's actually a whole whack of transitional densities in between. So it's not really simply one thing, because very seldom do we have a pure, a homogeneous spill of one contaminant. Even gasoline's made up of many compounds, diesel's made up of many compounds, so is bunker C. A lot of the chlorinated solvents have multiple compounds, so it's not just one thing, all right? But anyways, because of their immiscible, they tend to be absorbed into soils and or they're attracted to one another. Do you want the camera on? No. Can you see this one?
Yes.
Okay, sorry, I just got asked a technical question. Just wanted to make sure it was okay. So again, like I said, because they're immiscible, they can often they'll be absorbed, and then there's a lot of cohesive attraction between the LNAPL, DNAPL molecules, so they actually will become like little globules, or you'll have ganglia when you're talking about chlorinated solvents. Anyways, they can get trapped in pore spaces, and once they're in those pore spaces, their surface tension is about 21 dynes, and the surface tension of water is about 73. So interfacial tension takes over, not surface tension, and they actually get stuck. So if anyone on this call that's ever been involved with unconventional gas, like natural gas, one of the largest challenges they have getting that gas out of that rock is a lot of the gases get trapped because the water holds it like imagine like a plug on a champagne bottle or on a cork on a bottle of wine. They have to kind of break that down or move that to help get that gas out. So I'm going to show you guys ways of actually manipulating the behavior of water and the behavior of these contaminants. But they do have a tendency of behavior, and that's important on understanding that, so how we investigate and remediate sites. We all know we have spills. Typical sources are an above ground, below ground storage tank spill, pipelines, also truck rollovers. There's even been cases of sabotage that have occurred, and I've seen that internationally. There's been offshore spills. So there's a lot of different sources, and quite often they're accidental in nature, and when they happen, they can impact the soils. If they move through that soils as a pathway, they can impact groundwater. Depending on if they're a floater or a sinker, will dictate how they're going to behave, which you'll be evaluating during your investigation, and in deciding how you want to remediate that. This is an interesting bailer from a site that we dealt with near Melbourne, Australia. There's floaters, sinkers, and in-between density compounds in that bailer. Okay, I know that because we did some centrifugal tests on it and whatnot, and actually profiled what was actually in there. So it's not always just simply a floater or a sinker. You sometimes have many different things in that. So it just helps you understand their behavior. And when you're looking at the behavior contaminants, it helps you determine how you might want to treat them. So I actually came up with these drawings myself, and basically the brown area is obviously the soils. The white is showing vapors. We got water, and then we have contamination, whether that's LNAPLs or DNAPLs that are in there. They can often become trapped, and that interfacial tension really becomes an inhibitor. Of course, you can do pump and treatment, multi-phase. You can try biological programs, chemical programs, but if you don't make contact, we know you're going to have a great deal of difficulty treating those contaminants. So what we try to do is by changing the tendency of behavior to absorb or form globules to become more miscible in water, we're promoting solubility. We'll show you how we change the behavior of water, and also because we can also overcome that interfacial tension between those gas and liquid phases or a solid phase from absorption, we can actually increase the availability of these contaminants for you to remediate them better. And again, when you're dealing with this, interfacial tension becomes a major consideration on the behavior of these contaminants. And again, when these contaminants get in there, whether it's gas and or globules of oil or absorb phase, they cause pathway interference. And if you want an analogy, imagine you got 6 or 7 piers for a bridge going across a river. What if we double that from 6 to 12 to 18 to 24? Again, we start to block the ability for water to go through. Well, when this stuff gets trapped in there, it actually interferes with pathways. And sometimes the pathway, instead of being the shortest distance between 2 points, starts to be this elongated or more cumbersome pathway that results because this stuff's trapped. And when it's trapped, it can be a source of rebound later. Just showing the NAPLs and the vapors. This is a really funny drawing that I came at. We've all probably gone to a bar and ordered a drink, and you have a really good mixologist, I like to call them, and they'll make you a drink where you have 2 or 3 layers in it. Essentially, they're taking their time and they're playing with the density of things. This is kind of funny. We had a ping pong ball floating in lamp oil on top of rubbing alcohol. There's a soda cap floating in there, some vegetable oil on water. There's a bead floating in there, some dish soap, and there's a cherry tomato floating in there, some dye, milk, some maple syrup. There's a popcorn kernel in there floating, corn syrup, honey at the bottom, and a bolt. Just to show you that there's a lot of different things that we would call organic liquids, and some are polar, and how they tend to behave differently. And that affects the behavior of movement of things. So density is a guideline, but don't go think it's a floater, it's gonna run up to the top, or it's a sinker, it's gonna run to the deepest point in your soil or groundwater regime. It takes time. And this tendency of behavior isn't going to happen really fast. It takes time to move. So all I'm showing here is this tendency of phase partitioning. So a lot of petroleum hydrocarbons, although we do get some solubilities to parts per billion, which is harmful from us from a toxicological perspective, as an organic chemist, I can say their solubility is nothing to be super impressed by. Salt's way better, sugar's way better. Many things are much better dissolving in water than most petroleum hydrocarbons or chlorinated solvents. Unfortunately, they're toxic if they do get into our waterway, so it's a concern for us. So this tendency of behavior helps us identify where they're going to be when we're doing investigations and remediation of sites. And they're just showing some typical images of projects we've been involved with. Now, when we're dealing with something like sorption, on the left-hand slide, I'm showing typically sorbent compounds. It could be a little bit of free phase in there. And it's not really out there in that mobile phase in the pore spaces. And because of that, it's less available for physical, chemical, and biological treatment. And those are the only 3 options you have or combinations thereof. That's it. There's nothing else. So if there's anything you can do to desorb those and get them into that pore space, they become more available, okay? They may partition between the solid phase and that aqueous phase, but you want to get them in there. And if you can, like with a multi-phase extraction, you can pull vapors, dissolved phase, and free phase. What it's trying to do is enhance the desorption to recovery. Well, if there's something you can do, such as using the IV salt surfactants to desorb, make something miscible that doesn't want to be, it helps increase the availability of these compounds. And in doing so, we would say as chemists, you're creating their reaction kinetics, or I would say just their kinetics of availability. And this whole issue with sorption being a major concern is not new. This is going back to me. I remember hearing about it a little bit in the late 80s, but particularly in the 1990s. And this quote's great because it comes from 2005, but it talks about, during the past decade, much discussion is centered on the unavailability of sorbed compounds to soil microorganisms. It's now generally assumed that desorption diffusion of bound contaminants to the aqueous phase is required for microbial degradation. So if anyone's out there done any ex situ bioremediation, it's gone really well. You're probably dealing with F1, F2, maybe some light F3, but if you're getting some of that heavier F3, F4, you might notice it's lagging or slowing down. It's not that that's not highly biodegradable stuff. It is, lots of energy, bacteria like it, and they're capable. It's just absorbed, so it's less bioavailable. So if you can overcome that, you can actually push that along. So we've helped a few companies with that. But again, you got to manage all those other variables that help push that biological process along. So when things are absorbed, basically it becomes less physically available for multi-phase extraction, pump and treatment, less biological available for aerobic, anaerobic, or facultative degradation, and less chemically available for chemical oxidation and reduction type treatments, okay? So the cool part that we're gonna show here with IV salt is how we can overcome that solubility issue and get that into that mobile phase so that's more available. And what this slide shows is, you can imagine on the left is a NAPL or absorb phase. And what IV salt does in a very selective manner is like to say, a lot of the molecules out there have an ear, a nose, an arm, a hand, a foot. So we want to have some regional specificity in the sense that we have some selectivity. So what we're putting in will actually target the hand of a molecule or the ear or the foot. and bring it in, because as we know, gasoline is quite different from diesel, which is different from motor oil, which is different from bunker C. So we've changed our formulations in light of that. And the one thing that we've been able to do is even applying our stuff at very low concentrations, often 1 to 50, we're reaching out just to grab one of the hands of molecules to pull in the solution. As you can see on the far slide, we're not causing emulsification. You do not need to. And the good benefit of this is if you have an oil-water separator, it still works, activated carbon works, MySlex works, membrane separation, bioreactors, and we've been paired with all these. And our clients in the United States, if they exceed their discharge permit after the treatment system, typically the minimum fine per day is $10,000 US. So, and we've never had that happen. So we don't interfere with water treatment systems with our stuff. This is just a pop-up showing how typical surfactants work. And I didn't see that as being beneficial. So it was back in the 1990s, I did approximately a 4-year research work with project with a university to come up with this submicellular way of bringing things into solution so we could preserve their availability. And your body does a little bit of this, by the way. So as I said, because of the difference in the makeup of a gasoline versus diesel or other types of products, motor oils and bunker C, we've developed different formulations, even for like chlorinated and brominated solvents. And we have a new product called PFAS Sol, which we're actually getting tested by some people. One organization is actually in Edmonton. They might be on this call and this webinar. And there's another group in the UK that are actively with sites. They have PFAS and they're looking at ways to help desorb that and make it more available. So we're working with them. And another product we developed is called Deconit, which actually meets the ASTM standard for the decontamination of equipment. So I might show a slide on that later, time permitting. And again, like I said, because of our selectivity, you do not need to put this in a high concentration. So I used to have the saying, everyone used to tease me, I call it less is more, less is more. So I'm often saying to clients, try, if you really want to be aggressive because you have a lot of free product, you might do a 1 to 25, but try to ease that towards about a 1 to 50. And they find as they do, they find the performance is really good and they're obviously stretching the product and it becomes even increasingly cost effective, even if it is already at a higher concentration. Now I talked about taking contaminants and desorbing them, making them miscible so they're more available, but I talked about water, and water has a surface tension of 73 dynes. Now, in this little droplet you're seeing, it's a drop of water on sand. That's a fine sand. How come that water is not going into that sand? It begs a question. So what I often say to a lot of people is when you're looking at something like this, what you see at the macroscopic level speaks to what's happening at the microscopic, or in this particular case, the molecular level. So what's going on? And I'll often say to a crowd, someone in the audience, tell me what's water? They'll go, it's H2O. And I'll go, no, it's not. And they'll look at me kind of odd. I said, let me explain to you what it really is. And as I do, it'll make sense to all of you, okay? We all know that in the upper left-hand part of the periodic table, those are electropositive, like, H+, Na+, Ca+2, things like that. Way over in the upper right-hand corner, we have oxygen, sulfur, chlorine, fluorine, things like that, electronegative, okay? So as chemists, we just kind of put these delta symbols on things like that. So you can do that with a water molecule. And because of that, you can see that it's highly polar, okay? And because of this, you probably were told this in high school and university, one water molecule, the oxygen will be attracted to hydrogen in the next, and they call it hydrogen bonding, which gives that attractive force. And if you've ever done a belly flop in the water, you've felt it, it hurts because there's quite an attraction force there. And because that attractive force is so high, that's why it takes 100 degrees centigrade to boil, or 212 degrees Fahrenheit to boil that water. It's a lot of attractive forces to overcome, okay? So that's usually where we stop, but I'm gonna show you right now, it doesn't just grab onto the neighboring molecule, it sort of aggregates and keeps going out. It's because it behaves very much like a magnet. You can use that analogy for the behavior of water. So as it reaches out to its neighbors, north, south, east, and west, it does so in a very organized way, and it forms something called a water cluster. So this is actually showing you what you're really pushing and pulling through your geology. And obviously the finer the geology, the finer those openings or pore throats and that effective porosity, that if you have it, it's harder to pull those things through. But if you can have the IV solid desorbing things and changing the behavior of those clusters so they're smaller, all of a sudden, instead of that water being retarded moving through or reduced transmissivity moving through the geological unit, the K, while we're present, or as some of the Europeans call it, the apparent K, improves while IV solid is present. So we can desorb some things, we can change the size of the water cluster, so we can actually move what we've made available better physically, or help make it more available to the biological or chemical systems that are in play. And sometimes it was done sequentially. So this illustration is showing, imagine a water cluster trying to get in where you have some chlorinated solvents or petroleum hydrocarbons trapped in there by interfacial tension. So access and regress becomes a really big issue. So again, I'm talking about flow. And if you can't get access into those areas, those contaminants sit and reside, become trapped, and become a source of, we call back diffusion, matrix reflux. Anyways, you'll get the reoccurrence of contamination at sites and wonder why. Or we'll see sites, and I talk to people all the time, you know, we had no free product and then it came back because of a fluctuation in the groundwater table, and I'm nodding my head going, yep, you know, it's getting kicked out a little bit. So you need to get that stuff out to truly close your site, because if you file for a closure and that site has a reoccurrence of contamination, in the United States, it becomes somewhat of a legal and publicity concern. I've been on some major sites, so getting that out once and for all becomes very, very important. So in this slide, I'm just showing, imagine those large clusters getting made smaller and smaller. So now we have access. So we can start to work on those contaminants, make them miscible, so that maybe you're using multi-phase extraction or a biological or chemical program. You can then have access and regress, or at least interact with those contaminants in a more effective way. And this doesn't matter if you have sand and gravels to silts and clays. And quite often, as we all know, in Canada, unlike southern United States, we have a lot more silts and clays in our geology. There's a few places we have sands, but not enough. So we tend to have some very challenging things to deal with. So you have to do whatever you can to improve your options or your strategies in the, I call it the remediation game. And as I said, interfacial tension becomes an issue, and we want to get that stuff made more available. So what I'm trying to show right now are 3 animations, and these typically show what we do at sites where we're doing in situ remediation. Again, it could be vapor intrusion, it could be any type of petroleum hydrocarbon, chlorinated solvent, brominated compounds, fluorinated, insecticides, and other things, even organometallics. So let me see if I can get this to come up okay. Hopefully my narrative and what you see match. You'll often go on your site, you do your investigation for vapor, soil, and groundwater contamination. Based on what you see on that site, you know the depth and its 3-dimensional kind of placement. We often will say we can design a vertical injection well screened across that smear zone. And what we can do is, you see we put the circles around them, we know we can influence a certain area, so we can do the injection with the packer or just cause mounding, so we can actually address that smear zone. We inject it, it diffuses out at a certain distance, so we have a bit of overlap between the circles that you saw in the first part of this, and then we wait 24 hours and then we pull it out. So we refer to this as a push-pull process. And what I'm actually simulating is like a sequential extraction. Not so dissimilar from what the lab does when they're using solvents to extract your contaminants out of soil or groundwater samples, so they can give you a value of what's in the sample. So what I'm doing is, with each push-pull event, we're removing a certain amount of that mass. We're opening up those trap pore spaces or pathways and allowing you to get those contaminants. In this case, there's no need for a pump and treatment system. I have some clients who will do this and then they'll turn on their multi-phase extraction system, or they'll remove the LNAPL and then go to a biological or chemical oxidation system to finish things. Another scenario we get involved with is where we have to establish hydraulic control. Oh, hang on here. We have to establish hydraulic control because maybe the plume's moving and we have a sensitive receptor. It could be a stream or a creek, it could be a wetlands, it could be somebody's wells nearby or an aquifer for a city. So in those cases, you'll establish a recovery well or multiple recovery wells across the site to establish hydraulic control to contain and control the spill, because it has certain behavior and you guys want to manipulate that. And then working around that, say, central recovery well, we can put in injection wells, which are introduced in the IV sol within that smear zone of contamination that you've identified during your investigation. It's making contact, desorbing the contaminants, changing the behavior of water, so that the transport mechanism of getting it from where it's at to that central well for mass recovery is made a whole lot easier. We've not only done where we've injected from the outer 4 wells to the center well, we've actually, I've got a case study I can show you from Vallejo, California at an AT&T site where we injected at the 4 outer wells and pulled to the center. So sometimes, the center, and we pulled to the 4 outer. So sometimes the scenario changes for a variety of reasons. In that case, it was a lot of fine-grained geology and fractured bedrock. In this scenario, is we know that there's a lot of sites where we have pipelines, fiber optic lines, or even a roadway or a building. Well, these become physical obstructions for what we can drill and work on a site. And that's just part of what we have to deal with, those logistical challenges in remediation. So in those cases, if you imagine kind of in that center part of the screen is that obstruction that's there. So we'll go on one side of it, could be a roadway, a building, a pipeline, and inject our products under hydraulic influence at those extraction wells that you're seeing on the right-hand side of the screen. And what we're doing is, as we put it in, we're making desorbing the contaminants, change the behavior of water, make it more available so that those contaminants can be transported and recovered at those recovery wells. There's again like cases where we'll go in and do this using one of these three animation scenarios, and there's 4 or 5 that we typically end up doing or modifications thereof. And after we move the LNAPL, a lot of clients will stop and go to a biological or a chemical oxidation approach, or under the right conditions, natural attenuation or a risk assessment. So we see a lot of different things happening. So sometimes we only start the process, we don't necessarily finish it. So what I'm going to get into right now, I've got about 20 minutes with you, so I'm going to take some time to just walk through 3 case studies with you. This one's kind of interesting. It's a Superfund site in New York City. What they were dealing with there's 6 actual areas on this site that were contaminated. You can see an air photo here. It's about 130 acres in area with 6 major contaminated areas within that larger area. And they were doing a variety of different remediation. So a company called RU Engineering in the New York area had heard about our technology, and they were running a multi-phase extraction system in one of these areas. And they'd recovered a lot of mass, but obviously their rate of mass recovery was getting reduced because essentially they recovered all the available vapors, dissolved and free phase, but they just couldn't reduce the free phase anymore, which was one of their objectives on this site. So they got a hold of us. We did some bench scale studies, but there was a complication with this site. And the complication was, you can imagine with a lot of rail sites, there's a lot of materials that have been moving through here over the last 100 years of service. Not only do they have some of this mid to heavy end petroleum hydrocarbons, they had PCBs in the soils. And as everyone on the call knows, your allowable limit in any jurisdiction in the world for PCBs in soils is much more forgiving than your allowable limit in the dissolve phase. So the concern here for these guys, because of our selectivity, was they wanted to show at bench scale we could desorb the petroleum hydrocarbons more readily and leave the PCBs behind. And we showed with 4 to 5 orders of magnitude ability to get the petroleum hydrocarbons off the soils and not touch the PCBs. So that was critical for them in considering this as one of the options they were dealing with. And what I also like about this case study, it's a case where I'm going to show you where you can pair technology. So I've been saying this for a long time. There's a lot of tools in your toolbox, and like medical doctors and other people you're dealing with, sick patients, our sites. And sometimes we try more than one technique to bring that site or that patient to a better place, because we're always dealing with remedies, okay? So that's the site will speak to that. This just talks about some of their objectives, but the key thing they really want to do is get that free product out for a lot of risk reasons amongst others. And they wanted to redevelop this part of the site for high-speed trains and an area where they want to be able to work on them, okay? So this shows the dual phase vacuum extraction system. What I like about these systems is a couple-fold, because I know about the tighter geology we have in Canada, and in this site, it's in the northeastern United States, it was glaciated too, is that even at low flows, sometimes at liters per minute, you can still establish very good hydraulic control over a plume, vapors, dissolved and free phase. And they actually could show that here. So even though they had some finer grain geology and it was quite mixed, they showed that ability. And this is just an air photo of the same site, and you can see some of the multi-phase extraction system. And that kind of linear building going up and down the bottom left with a kind of gray roof, that's actually their treatment system. So they had oil water separator, activated carbon, and they had a discharge permit that they had to meet. And as I said, we didn't cause any challenges for that system. But like any client, when they bring you in from bench scale to full scale, they picked some wells they wanted to do the pilot scale application on, okay? So they actually were gonna pick 8 wells, which I'll talk about in a minute. This slide's interesting because it talks about what I said earlier, that they ran their multi-phase extraction system. These guys did a good job. They got 1,883 gallons of product out. If you want that liters, it's 3.78 times that for liters. So they did a darn good job. But the interesting part about a lot of these systems, particularly multi-phase extraction, 84% of that recovery happened in the first 5 months. And this is going from 2013 to 15, okay? So it becomes asymptotic conditions end up being results. So the performance return ratio, as it were, or return on investment, some people like to say about this stuff, it starts to wane after time. And I've seen people pull their multi-phase extraction systems. So I say to a lot of people, if you've got it, don't pull it. See what you can do to enhance it, because they're really good systems, okay? Again, for vapors, dissolved, and free phase, they just got all the stuff that's readily available, that 84% in 5 months. It's just that other stuff that's just stuck in there they need help to get at. Because once it's free, these guys will definitely get it. So I talked to you guys before about how the IV-Sol works selectively, whether it's on a free phase, zorb phase, or dissolved phase, keeping that in that kind of available state, okay? So that's really what they were honing in on here, to see if by doing that, we could then get in that spore spaces so that the multi-phase extraction system could then latch onto it and realize that mass recovery rather quickly, and hope to expedite this site remediation. So this shows 8 of the circles actually within them are 8 wells that they were just, no matter what they did, they couldn't cause any fluctuations or reductions in mass. So of course they want to give you those during the pilot, but we also suggested if they had some challenging wells, they're probably the ones we should kind of test drive this on. So basically over 1 week, I think it actually happened over 8 or 9 days, because it had some reason why, I'm not sure, but I think it was something about access to the site because of Amtrak. The 3 applications actually end up having over 8 or 9 calendar days, but basically a week. We typically do it from Monday to Friday. We did 3 applications of push-pull, inject, wait 24 hours, and then pull. Essentially, we do the injection, and then they would actually kick on their multi-phase extraction system to do this. In some cases, we injected at the well and pulled from the same well. In some cases, because some of the injection wells were on the other side of railroad tracks, we'd injected that well and then pull that underneath the railroad tracks where the contamination was to a well that could communicate with it to see if we could enhance mass recovery. So we call that a sweep. So we did a couple different things here because of the large area nature of this site. This in the top just shows them doing the injection, no pressure. I would say easily 80+% of all of our applications are done without pressure. On the few sites that's done with pressure, the very good injection applicators that we've worked with in the United States are very smart about injection to avoid daylighting and also not cause any fracturing, things like this, unwanted that is, to get good delivery. So pressure can be good, and things are really deep, pressure can be actually quite helpful, okay? So just showing them doing that injection. Again, like I said, we did 3 applications over that week. And now there's a saying, if you can't monitor it or measure it, you can't manage it. And what I'm showing in the bottom right is just a picture of our surface tension test. So imagine you injected at a well that's imagine it's 10 meters from you and you're pulling at a well where you're standing. Well, you can actually use this test to see exactly when the surfactant carrying those contaminants is arriving. And it's a real-time test, very inexpensive. So we make this available to our clients and they really like it. You can still send samples off the lab and get them analyzed, but we know you won't get the results until next week, and it's probably going to be somewhere in the vicinity of $100 a sample. This is like pennies per sample. And there's just showing a bead of water without any surfactant. And in the background, you're seeing a very well-rounded, very well-arched bead of water, but there's just a trace of surfactant, so we're starting to behave different. So it's really easy to see. And so it's quite nice. And we've had clients do not only use our test, but actually send off-site samples to see what the correlation is between the tests on our sheets versus the lab. And there's a 96.7% correlation, as was determined by one company for one of these more litigious projects we're involved with in the United States. This is an interesting slide, and it shows the thickness of product at these 8 wells that I talked about that were troublesome and the thickness afterwards. I like to show it another way for fun, is the percent removal. And this is showing it there at those 8 wells, so it's quite significant. And we had an average in that week of 81%. What's really particularly interesting is that when we did that work back in late October, the last week of October of that year into the beginning of November, so we did the work. We were then, they applied to go to full scale with the regulator, as they do. It took a long time. And when they retested all these wells, there was no rebound in thickness all the way to July of the following year. And it was after that they got to go to full scale. So just showing what we removed stayed out. So that was really nice. But again, it was a case where we desorbed it or it made the LNAPL miscible, where their multi-phase extraction system did a very good job of pulling it out. So that's a great case of pairing technology, because 1 + 1 can equal 3. So conclusions were quite nice, that we did help enhance their separated phase hydrocarbons, is a term sometimes used for LNAPLs. That was great. They really liked the fact that what we did from injection to recovering, that time cycle was rather short, 24 hours. I have some clients that'll do 48 in some cases. They did try some concentrations up to 1 to 20 pretty high, but I'll be honest with you, I got them to go towards 1 to 50, and they had to agree with me that was the way to go. So that was really good. And again, you saw the results in those slides, so they were very pleased with the results, and we went to full scale. I'm happy to say in literally single-digit months, we cleaned up the entire area. It's been redeveloped. What was funny for me on this site was I was talking to staff, and we're still selling more, drums of product to them. And I was like, God, things mustn't be going very well. They're buying more product to clean up this area. I thought it would be done by now. I called up the project manager, and she starts laughing. Bud, we've already cleaned up the area. We're now using you in the other operational units on the site, because once we got approval to use it in this one area, they could use it wherever they wanted, essentially. So that was a really nice, feather in our hat that we did a good job. This case study comes to you from Daniel Hirth from Blue Sphere Environmental, and it's a site near Melbourne, Australia. So I've abbreviated the presentation to show you today, because I've got 3 to show. The last one is actually an upstream site in Alberta. So if anyone's familiar with manufactured gas plants, they would receive a lot of these materials, and then through a lot of distillation and chemical processing, try to break them down to make lamp oils or other types of oils that people were using back in the day to do, anything from products for household to industrial greases to you name it, everything, right? So yeah, so there was, unfortunately, back in those days, they were less concerned about spillage and stuff, because they didn't realize the impact of the environment. So that's what happened at this site over its approximate 100 years of operation. What this slide shows you is a number of areas with free phase, and pretty much where they had naphthalene impacts, they had LNAPL and DNAPL, or these multi-phase type contaminants that were there, and they were having a hard time cleaning up. So we did a bench scale study, and then we went to full scale and to help these guys out with that mass recovery. The key thing about this that I find when I'm doing these applications is with clients, in the first case in New York, we actually were on site helping with the pilot scale. In this case, we actually spoke to this client every single week. We jumped in on their calls where they were reviewing what was going on. So we had that ongoing dialogue, just like a doctor and a nurse and a medical team evaluating the patient, making small tweaks and whatnot to make sure that the remedy or outcome is positive. So that was really, really good there, right? So their objectives on this site were not only the NAPL, but a variety of different benzene, ammonia, cyanide, amongst like this. And they wanted to remove that, and obviously remove that risk as a source pathway receptor. And you'll see that there's even a residential area not far from here, right? They had over 100 wells and some depth to the water table. And again, like anything, they have some finer geology in this site. And again, there was just some challenges, and we were able to get some of this tarry material out. I've spoken to you before in the last 2 case studies about how the IV solid works below the micelle level, and we were able to get those LNAPL and DNAPL contaminants in the miscible phase, so that they're essentially more like a multi-phase extraction system was able to get that out, and they were quite pleased with the performance. And they had to do a lot of tweaking, because they were looking at residence times of 24, 48 hours, and they actually ended up finding somewhere between about 4 to 8 hours from application extraction end up being the winner for the site. Although every application worked, that seemed to be the sweet spot. It's just showing them the site, one of the areas that they're working. You can see around there's some residential, even some agricultural activity, and them just doing their work. So the contractor was Enviro Pacific. These are kind of neat. Over that course of the 6 months of application, the balers came back with both floating, sinking, and in between. To eventually we got most of that out, and then we're still dealing with very little, more like a DNAPL or denser materials. And as you know, some of those heavyweight petroleum hydrocarbons sometimes are sinkers, although you might think they're going to be floaters, they're not always. And they're just showing a jar with a little bit in there. So over that period of time, there's successively less and less and less mass for removal. So we were always heading in the right direction. But again, that continuous conversation and tweaking. This is a nice plot that was provided to us by Daniel, just showing their mass recovery that they've got, daily recoveries and total recovery over time. And you'll notice sometimes it changed because they were tweaking things. They were attacking some areas harder than others as they were starting to clean up things. certain areas, oh, we're done here, so let's put all of our energy over there. So these guys are really clever about it, and they really took it, they championed the project and how they were very creative about doing things. And again, that kind of weekly dialogue allowed us to kind of do these baby tweaks and do things. And again, we arrived at that 4 to 8 hours seemed to be the winner for this site. You know, I think part of it is they're heavy compounds. We made them miscible. So while they're kind of miscible, we wanted to get them out versus maybe they might resorb or they might get trapped. You know what I mean? That kind of thing. Just showing some slides over the period of time that they provided to us. So that was nice. Yeah. So the conclusions were they found to be a viable remediation method for removing that type of LNAPL contaminants they had at the site. There was limited human and environmental receptors. They found that it was sufficient, effective for the permeability that they had for the NAPL, which is hard to get things out. We got that out. They liked it was sustainable. It was really cost effective compared to a lot of the other alternatives they used. A lot of things didn't really work very well on these type of things. No noise, no odor. They had no complaints to the locals, and they were very good about communicating with the local, shall we say, population or residents about what they were doing, what they were up to, and they found that dialogue always keeps the local residents quite happy. We're biodegradable, non-caustic, non-corrosive, things like that were all positive. Anyways, long and short of it, the site was turned off in January of this year, and they're into their closure phase. So it's a nice story. The last case study, we're going to tell you guys over the next 5.5 minutes as I pound through these slides. It's a case study that's actually in northern Alberta. And we have oil and gas activities in Alberta and BC and Saskatchewan. So this is a nice relevant one for us. Back last summer, there was a 320,000 liter spill in northern Alberta. So I'm going to talk to you about that and how we got involved with that project. And Earthmaster was the environmental consultant involved on that, taking care of those activities. Okay, sorry. So here shows, hey, a typical view of a facility that you would see most anywhere. In the bottom foreground, you see kind of a red outline. That's actually kind of the bermed area, the containment area. So when that spill occurred, it actually went into there and actually breached it and ended up going down the hill. So again, I told you it was 320,000 liter mixture of crude and oil products. Fortunately, because of the system set up on site, they actually managed to contain and control about 99% of the spill. Unfortunately, there was about 300 cubes already inside the containment area, so a certain amount breached it and went down the slope, okay? And I'll give you some details about that in the next slide as far as the slope. And the big concern there is source pathway receptor. Not only going through this vegetated area down a slope, at the base of the slope, there's a creek, a fish-bearing creek. So that's a big concern. Just an outline where it was at. This is actually some nice drone shots, courtesy of Earthmaster of the site. And you can see that there's some oil that's still in the burned area, but it went down that slope as we discussed. All right. So they were retained, Earthmaster Environmental Strategies was retained for the project. The key contact I have there, if anyone knows Adam Dunn, feel free to speak with him after this. If you pose some questions about this case study that I can't answer, I will probably collect those and speak with Adam and get you answers afterwards. Okay. The challenge here again with that spill is it went down a 20 to 30% grade slope, but 180 meters towards this fish-bearing creek, which is a real concern. The release consisted of about 66 cubic meters of oil and 254 cubic meters of salt-produced water. Fortunately, there was no salt impacts along the pathway, which is great, but the contaminants concerned were typical F1, F2, F3, BTEX, things like that. The highest concentration observed in the soils was 43,000 or 4.3% contamination. Okay, and again, the receptor of concern here is that fish-bearing creek down below. So there was some challenges with this application. And as everyone knows, when you're dealing with Alberta, when it decides to rain, it rains. So shortly after this occurred, there was a 150 mil rain event that was going to occur. So it creates some issues. They put some bell holes in to contain and control some of that spill so it wouldn't impact the creek. And they also used this thing called a light detection and ranging, which allows them to use lasers to see if the spill went beyond their bell holes, and they contained and controlled it quite well. Very good use of field technology. And those bell holes became helpful in the application that we actually did. When they were looking at different applications, so we can always dig and dump things. That's one of our options. But there's also merchantable lumber on this site. So if they decided to clear cut and take all that, that'd have been about a $50,000 cost. Bioremediation could have been done, but it wouldn't have addressed, the movement of the plume, and it would have taken a long time and a lot of ongoing monitoring. Stoichiometrically, when you have a lot of contamination, chemical oxidation can be expensive. When you get rid of like the free phase, then it can be more practical. The other concern here is the killing of vegetation and things like that, and some PPE, and that it's a TDG material. Okay, so the remedy chosen was Ivy-Sol. So getting into that really quickly, I talked to you guys about how it works. Fortunately, the impacts to the site were relatively shallow, so that flush application was done, and Alberta Environment accepted this for use because of a lot of the characteristics about our products that I've mentioned before in the previous talks. Just to say that Alberta Environment approved it. I'm going to snap ahead just to get into a quote that goes at top. If you can't monitor it, you can't manage it. That came from a regulator in Connecticut that I dealt with 19 years ago, and I've always hung on to that, and it really affects what I do. So when they were doing the application, the first trial, they tried about a 1:30 ratio using backpacks to try to clean things up. Well, that didn't work so well. It wasn't enough volume to get it to the bell holes. They tried a next application at 1:20 using high pressure, but that caused a bit of splattering and things like that, so that wasn't the best. Then they went to about a 1:40 ratio. They found that was better. And at the end, they optimized from what they learned from the first three things, and we're talking on going to about a 1:60 to 1:80. I think a 1:57 was the best result, and they found that to be quite good. So little went a long way. And as I said, the observable cleanups, when they cleaned up an area before and after, was very pronounced. They could see the benefits, and to get the stuff the bell holes for easy mass recovery. This table shows you some of the before and after numbers. You see someone up there, 18,000, 43,000. The before and after were very significant, so we're very happy with that. This is a before and after that happened within days, so that was great. You can really see the difference in vegetation. The vegetation responded rather rapidly after they removed the contaminants. Nice testimonial here. In July 2019, we were faced with a 320,000 liter crude oil produced water spill at a facility in northern Alberta. With our spill response strategy, utilizing innovative Ivy-Sol surfactant remediation strategy, we achieved significant time cost and environmental cleanup benefits, resolving 99% of the spill on the hillside. We and our client were pleased with the outcome. So really happy about that. If anyone's got any questions on that, they can talk to Adam Dunn. So that basically gets, the last slide I'm going to show is this one. So when clients contact us, we ask for a one-page site evaluation form. From that, we can kind of model your application, whether it's in situ or ex situ, and we can determine, what product that you need, what dosage you need. We put the proposal together, and that fifth, going to 6th and 7th step, is that ongoing support and technical interaction that we do with clients. And I'm just going to click forward now just to get to the contact slide for people that are trying to get a hold of us. As you know, Jean Perret, a lot of you know him already. There's his contact information, so you can speak to him or myself. And there's my contact information. And Joe, I thank you very much. I went about 20 seconds over time, but thank you everybody for your taking your time to listen to my talk. Thank you.
Thanks, Bud. Thanks for that. A lot of great information there for everyone. And thank you, Ivy International, for sponsoring today. If you have questions, please feel free to type them in the question box, and we'll get to as many as we can in the next few minutes. A reminder that the presentation will be available later today online at isa.org/webinar, so I encourage you to check that out. Okay, Bud, I'm going to start the question round.
Okay.
How is the product applied efficiently, and how can we control the dissolve phase within a certain allowable level?
Yeah, so as I said to people, we advise clients to apply our products at like a 1 to 50 dilution. If they have NAPL, they can try to go a little bit higher, but if you're finding low levels work really well, that's great. Because we don't have to emulsify, that's why I say go at a lower concentration, which also means that the amount that we're dissolving is relatively limited and controlled. Okay, there's a relationship there. Because our surfactants are non-ionic, we don't cause a lot of dispersion in the area. We get things, miscible in solution. We don't cause it to go 5-6 meters away. You'd have to drag it through a pumping well to take it that distance. So it's more of a local thing. So it's actually quite easy to do it. The second thing is by having our field test kits, it allows you guys to see what's going on and what the relative concentrations are in areas. It doesn't mean that you can't do other field tests or send stuff off to the lab as well.
Okay. How does the recovery well work? Does it collect contamination, or is it just the monitoring the quality of soil and water?
If it's an extraction well they're referring to, and say we're ejecting at one well and they're extracting at the extraction well, that well will be where that liberated mass will be recovered. And as I said before, we have those field test kits, so you can actually see when the surfactants start to show up, and as the beating of the water starts to lay flatter and flatter. Not only does that tell you that the peak of the surfactants coming through, but it's carrying more of the contaminants. So the feedback I've gotten from a lot of clients is they'll use these field test kits to determine, I've got 12 samples I've collected during the application, but only have a budget for 6 samples. They'll use this test to say, I want the beginning in, and they'll pick those samples, show it's going up, it's peaking and coming down. They can actually get a nice response curve from the client. So what we're really doing with the recovery well is where we're going to remove the mass. So over that area from the injection point to the extraction point, that's where you're cleaning the soil and groundwater. And if there's any vapor VOC contamination that you're liberating, that should also be recovered at the well. So
what happens to the collected materials?
So when those are collected, people are removing them. It could be by vac truck or pumping system. In some cases, it goes off-site because that's what the clients are doing. In other cases, they're actually treating it on-site through the oil water separator, activated carbon, MySlicks, bioreactors, air sparging systems. The list goes on that we've been involved with. And we don't need discharge permits with those.
Okay. Have you used hydraulic fracturing to increase the availability and more rapid removal of contaminants?
A little bit in the United States with some very nice effects, because the capacity of that technology, again, gives that value of 1, and our ability to desorb things and make them more available, call that another value of 1. When you couple those together, the results that we've gotten, Joe, have been very, very good, great insights. Even where people are injecting like that fine grain activated carbon, some stuff to kind of absorb things, we've actually had some of those contractors and they're actually getting better delivery and placement.
Okay. Many surfactants are quite toxic to aquatic life. Have your products been assessed for toxicity to aquatic life? And are there any restrictions for use of your products near surface waters?
Yes, we've had our products extensively tested, and a lot of that stuff's available in our safety data sheet. You'll find it quite involved, not just looking at impurities. The applications that I'm not a big fan of using surfactants for offshore spills, and there's a lot of journal papers on this, because you're taking that surface spill and you're actually putting it in the water column, which is affecting a lot of the fish and aquatic life. We have been used in a lot of like shoreline cleanup and near shore cleanups in those sense to remove a lot of contaminants. So we help mitigate the actual impact going into that stream, or in another case, actually into an ocean or a bay.
Okay. How do you address contaminants that are absorbed into the center of soiled lumps and not directly exposed to fractures?
That's a great question, because depending on how fine and cohesive the soils are, that actually happens. And for a lot of people that are trying to like situ bioremediation, there's clumping effects. Unless you're using a type of an aloo bucket that's often used in Europe, which is actually meant to really break down a lot of glacial clays, that stuff can actually get trapped inside of there. So unless you can give it more time to get penetration, that stuff gets trapped. So it creates a challenge, and the only weapon that we have and stuff like that is time. So if someone's looking at finer and finer grain geology, if we're doing an application, instead of like doing a 6 or 8 hour, 24 hour, we might do 48 to 72 hours. And the other thing you'll find, Joe, is when you're doing a site where you have finer geology, if it's in situ, your spacing of your injection wells becomes tighter, because you only go out so far into that formation, right? But it's definitely going to present a challenge. If you don't make contact, that stuff lingers and stays.
Okay. Doesn't look like there's any more questions right now, Bud. So if you have questions, please reach out to Bud. His information will be on the slides at the end. Appreciate this, Bud. Appreciate you participating. Appreciate your ongoing support of ESA and our events and everything. Reminder, there is one more webinar next week and one the following week, and then we're going to take a break for the summer. We'll be back in the fall with some webinars. Reminder that if you haven't registered and are interested, Envirotech starts tomorrow. There's 27 presentations. You don't have to attend them all. You can watch them later. So please take a moment to check out the website, esa.org/Envirotech, to see what's being presented, and hopefully you'll register or tell some friends, colleagues. We'd appreciate it. So until next time, thank you. Thanks for your continued support and stay safe.
Thanks, everybody. Stay safe. Bye.